We learned what one neuron can do with one input. Next, we'll see when one input is not enough. We'll try using two inputs and even a hidden layer. Prepare for some neurons in the shadows. Get it? No? Because hidden layers are... No. Gonna code, debug, and have fun. Coding with Radu. Coding with Radu. Gonna prototype and design. Coding with Radu. Coding with Radu. Let's code now. Open the playground from the link in the description. It should have here fwd_g as the session name. Now let's have the same network as before. So minus 0.5 for the weight and minus 0.1 for the bias. And the car is going to stop right here at this dotted line. Let's change the objective so that it goes up as much as possible. So can we figure out a network that lets the car go as much as it can before hitting the border there? And we could try playing with this. Basically, it's kind of logical that this needs to be a little bit to the right. So maybe moving the bias like this. This might be too much. Let's try it. Too much. We probably need to change also this, maybe something like that. I don't know. Still too much. This is tedious. We can also do something else to figure it out. We can use the genetic algorithm from phase 1. It's right here. Let me show you. When it optimizes here, it's going to try to create many different cars simultaneously. And each of them have a different network. How different from the one we started with is controlled by this slider here. So if I'm going to go down all the way and press this button again, you will see apparently just one car going up, but it's actually 100 or whatever going up, and this network is the same that we were playing with before. Here in this simulation, when the car touches the border, it disappears entirely because there are many of them and I don't want it to be too crowded. So let's try to give a little bit of a mutation here. And that means that the network is going to be similar to the one before, but not exactly the same. So now you can see that we found a car that is pretty much touching the border, but it didn't disappear. It's still here. So it's a good car. And when we find a good car like this, we press this save button. And now we have this new car to work with. Like if we close this optimizer from here, you can see it going up and then stopping exactly there, pretty much. Let's see close. Is it really very close, or could it go even higher? It might go even higher a little bit. Let's try optimizing again. Let's save and try again. Every time we run this optimization, the previous best car is not lost. So if it looks good, saving in the worst case, it's just going to give us the same thing we have previously. We don't lose anything valuable like this. So let's save again. And the last time, I just want to be sure that I'm getting as good value as I can get there. Save. I think it looks kind of like as before, so maybe it was good the first time already. And these values, minus 0.56 and minus 0.14. Let's figure out what this value is here. Turning on the calculator, and 0.14 divided by 0.56 0.25. So that seems to be the point here, 0.25. But this weight and bias are quite complicated. We already start to have now the second decimal there. And these are some things that we can expect from neural networks. They don't give us the easiest way to write 0.25 there. There are several easier ones that I can think of right off the bat. For example, here I could put minus 0.1. Now, if you press the 0 key on your keyboard, it's going to zero that. And lower like this, minus 0.1. And this could be minus 0.4. So zero that. Minus 0.4. So this should be the same thing as before. Let's try to restart. And it is, but it's a simpler one because 1 divided by 4 is 25%. So easier for us to understand the values, but the end result is the same. There are other values here that are easy to understand, like minus 1 and minus 25. For these small values, when scrolling, hold down the Shift key. This is going to make you scroll more precisely like that. So refresh. And this one works as well. There are many solutions here. The one found by the genetic algorithm is just one of them. And these, for me at least, are easier to understand when I look at the numbers, what is really going on here. Now, it's important to stop and think, what is the car really learning here? What is this function for? And one thing that can help with that is changing here the title FWD_B. And we get the same thing, but now the car is a bus. And you can see it doesn't work. The reason why it doesn't work is that the bus is longer. So the distance here from the center of the sensor to the tip of the bus is longer than we had before. So it is going to touch. We could run the same optimizer again and find a solution that works for the bus. So that's no problem. But the same brain that we had previously doesn't work also for the bus and for the previous car that we had. Let's save this one and now close, and let's see the bus going smoothly, and it stopped perfectly there. But if we go back now, we can see that the car is stopping not anymore in the last moment where it could stop there, because it's using the brain that we made for the bus. So this is important, how big the car is. And in some cases, real life cases, people are making the same kind of cars equipped with the same kind of brains, and then they have different brains for other cars that are different just because the car has a different size to it. If you want to have one brain that does everything, then the size of the car has to be an input here, an additional input. We won't be doing anything like that here. It's not very complicated, but I don't want to teach you about the buses here. I just want to focus on the cars. But basically, we need to be able to understand that a longer car needs to stop accelerating earlier than a shorter one. Now let's go back to these values here, minus 1 and minus 0.25, like this. Restart just to see that it works. And another thing that doesn't work is if you write here FWD_2. So we have the same car from previously, and it goes just as expected, but there's another car on the left, and both of them have the same brain. So, interestingly, the car on the left does nothing. Stop and try to figure out why. Maybe pause the video and think about it. I'm gonna start talking again in 5, 4, 3, 2, 1. So there are two dots here on the right. One is for the car on the right, the one that is moving, and the other one is outside of this region to begin with. So this car is so close that it's already inside of that black region where the neuron doesn't fire. So it's never going to start. If the car is too close there, it's never going to start. And you can really tell that something else is needed here. I mean, what happens if we do make this car move just like this? For example, we can lower this bias more, like that. It's moving, right? But if we restart the simulation, that means that this other car on the right is going to crash because it's going to stop accelerating much later. So we can't have them both, not with one input here. Let's see what happens if we introduce the speed as well. So here at the top, S is equal to SPD underscore 2. And now we have some extra things here. We're going to get to them in a little bit. But first, let's just put some values for these weights and biases. Let's put -4 here, minus 0.4, and minus 0.4 here as well. And here, minus 0.3. And let's refresh. And something happens, and arguably it's better than before. It's not perfect. This car is not going all the way till the end. This one is also not going till the end. It's worse than the one on the right, but both of them move this time. So it looks like something. Now, before we get into what is happening here, I want to show you a nice tool. This Desmos calculator has a 3D version now. So desmos.com/3D here. And let's write the same function we had previously. So minus 0.4x minus 0.4y has to be greater than minus 0.3. And you can see a flat surface here, this red region in the XY plane. Now, just a little bit of exploring here. This is the same thing as if you write minus 0.4x minus 0.4y plus 0.3 greater than 0, right? So let's write that. Plus 0.3 greater than 0. It's exactly the same thing. We just moved that one term. Now, if we remove the greater than 0, we move out of the XY plane and we're in 3D now. We are defining a plane. This now, what we have here, is not defining a line anymore. It's defining a plane. And only when we do that kind of comparison, like equal to 0 means the line where that intersects the XY plane there, or greater than 0 means all the parts of this plane that are above water, so to speak. So positive values. Now this 0.3 here is called the z-intercept. It's actually this point right here where the plane is touching this z-axis. Because if x and y are 0 here, then you get just that. So that's why it's called the z-intercept. And this here controls the rate of decrease, in this case on the x, and this one the rate of decrease degrees on the y. So this plane is tilted in the same way on x as it is on y. But if you would have here minus 0.8y, for example, it's going to be tilted on x less than it is tilted on y. It's much more tilted this way than this way. But let's go back to our original one. So minus 0.4y. And let's go here and have this XY orientation and zoom in a little bit because we are only interested in values between -1 and 1. Now, this is not centered really well. You can go to these settings here and say center origin. We can also make these surfaces translucent like that so we can see through it. Let's zoom out a bit so that this 1 appears here and -1 is here. So this, what you see here, is the same that what I am plotting here. I'm just using a little bit of shading here. So kind of like the plane going under the water there. You can see it like that. And there is a slider here at the bottom that actually controls how pixelated this image is. It takes effort, processing power to calculate this image right here. So I don't really recommend getting this smooth version from the left side, sticking to something like this and above if your computer starts to burn up. But basically this plane, where this plane is above the water, that's when this is going to trigger now. So if these dots appear to be on land, then that is going to trigger for them. And this mode also has a simplified view because this is showing a 3D space here, right? But we don't really care about what is going underwater. So if you click on this once, it's a simplified view showing just the part of the plane that is above water. Or you can consider it like that. So back to the 2D space coming after we have an inequality sign there. So let's rerun now the simulation and see what is happening here. It's very interesting, right? You should take a moment and try running this many times and paying close attention to what is really going on there. So this car on the left that is stopping early, it's this point. It's moving on the edge of this plane here and then somehow going down and stopping early. The other one, the car on the right, goes higher here and somehow slingshots away from this plane. Like it jumps from there, kind of. And it falls down later. Interesting, isn't it? Now, if you look at the top here, I can only show one of the two branes. They are the same brain, so the same value for this weight, the same value for that weight, and for the bias, but the inputs for them differ because now this one is closer, so it has a larger value for this 0.86. This is 0.86 here. This is going to be smaller, right? So the brane that you see on the right here is going to be from this car here. And if you turn on manual override, you can see that brane changing while I'm moving that car. And look at what the point is doing on the right. So I'm moving the car forward and backwards and forward and backwards. And because I'm changing the speed like that, it kind of looks like it's drawing a circle because it moves the point up and down, also below the 0 point vertically because the speed can be negative in this case. But combined with the sensor there is also moving it from the left to right. So somehow it's drawing a circular pattern there. Of course, if you would do this somewhere below here where this doesn't read anything, then that point just moves up and down like that because there is nothing moving it left to right. The sensor isn't picking up anything. And of course, if I'm stopped, then the point is just going to lie on the horizontal axis like that. So really, there is a lot going on here. And I recommend you play with this. It's really fun. But let's try to optimize this so that the cars go as much as possible. And let's use the optimizer from here. So hopefully we're going to get cars that are going to be as close as possible to the border there. And now we are getting something better actually. So let's save this and let's try again. Now, one thing when doing this simulation, the cars, there are two sets of them, right? On the left and on the right. They have the same brains. What I mean here is that the cars here are all a little bit different, mutated slightly, but exactly the same brains from this set are copied in this set. And the car showing in red here is the best one of both sets. So you might see here a car that is a little bit better still in front of this one and it didn't yet touch, but its counterpart from here, it's maybe below somehow. So the added distance that they traveled is less. Let's save and try one more time. Let's see if we can get it really, really close there. It's still doing something, so wait for it to stop before saving anything, otherwise it might collapse eventually. Let's save this. And I think I'm happy with this. It looks really good. Now let's close this and see just two individual cars. And it's nice. They are stopping there and they are doing some kind of crazy things here. But if you're like me, something bugs you at this point. The car on the right actually seems to arrive faster than the car on the left, which doesn't make sense. I mean, look at this. It's overtaking it about now and stopping it. Let me show you that again. So it's overtaking it now and stopping there. And if you look here in the diagram, this one is slowly making its way there, and you can kind of see the overtaking moment from this slingshot guy that just lands there where it should be ending. So the fitness function described inside of this optimization is go as far as possible, but it doesn't say anything about the speed. Like, it doesn't matter if they are going there as fast as possible or not. And integrating both of those in a fitness function is not easy because it's a kind of a two-parameter optimization function. So we are just going to not use the optimizer anymore, but I do want to show you still this. Like if we decrease this value even more, the rate of decrease on the speed here, it's going to move that plane kind of like that even more. So here, this apparent slope is going to go down like that. And refreshing now is going to make the cars start to do that even earlier. And now they have this really, really slow movement at the end here. You can go even further than that, like this. And now you see very soon they start doing that. And they start to really, really crawl there in a funny way. Of course, increasing this too much like this is a big problem, because this is going to make them slingshot like that really much. It makes them slingshot because they accumulate speed, and then the friction is not enough to slow them down on time. So there are very many things here to consider when doing this optimization, like how the slope should be here exactly. But the really important thing is this point right here where the car must stop. Let's refresh now. And we see that we got something good. So this point here is really important. It needs to be outside of this lighter region. So it shouldn't be on land, because if it is, then it's going to accelerate more, and that means that it's going to get so close that it collides. But now let's focus on the car on the right. Let's refresh, and it's this one. It's slingshotting. We kind of want it to slingshot more, right? So that it lands perfectly in that one spot. Could we do that? So I need this to be a little bit higher there. I think that's too much, so I'm going to hold shift and maybe say minus 35%. Ah, too much. So let's try minus 38% on this one. It's now doing that thing. It's fixing it, getting close. So it should be a little bit higher, minus 0.37 maybe. Let's refresh. Still doing that. 36. And now it crashes there. So it's not easy to figure out the exact values. We would need even more decimals there. Or we could play with this value as well. Increasing this is going to lower this a little more. Okay, now it stops nicely without it triggering anymore. It could still go a little bit higher. So maybe this one we try to increase a little bit. Okay, this is perfect for me. But let's now focus on this other car. What is happening with that? So you can see it doesn't go as far. And it even moves a little bit after that one has stopped, so it's not as good. Let's see what happens here. It's sliding down like that, right? And you can see it's stopping before the other car, closer to this 0 here. So that means that the sensor is reading a smaller value here. So it's further away from the border. We could get closer to the border if we move this a little bit like that. So we could go here and make it higher, but hold down shift. So let's make 29, and you could see it moved a little bit forward. Let's try 28. And the one on the right is also moving now, and it's too much. It actually collides to the wall. So let's just stick to minus 0.29 and rerun this simulation. And this one got closer, but it's still not exactly there. And it's doing that thing where it's sliding down the hill instead of jumping somehow, slingshotting like that so that it lands perfectly there. Let me run this with a higher quality here just to show you better what is going on, because that pixelation is interfering a little bit. Basically, we would like there to still be some land here so that this car can accelerate a little bit more and then slingshot exactly there. But there is a problem with that. You see, this other car needs this point here to be the border. So if that car needs that point to be the border, and the one on the left needs a point there, and this point here needs to be outside of that region, it's not possible to do this with one single line, is it? And that's where hidden layers come in. A hidden layer is a row like this where we can add more neurons. They're called hidden neurons or hidden nodes, if you prefer the graph terminology, because their computations are not usually seen from outside the black box. Now here we do see everything, but I still use the word hidden when I mean not an input or output node. More terminology. This is also called a perceptron. When we add hidden layers, it becomes a multi-layer perceptron. It's important to know this because some libraries use it. Like when we use neural networks in the machine learning course, we used the MLP classifier inside the Scikit-Learn library in Python. So good to know that means a neural network. Go up here and put underscore h instead of 2. Now go here and make sure that this pixelation is on, because we're going to change some things here and it's going to be slow otherwise. And let's do something. Click first on this point. And now you can actually create a new point here. And this one here connect to the same one. So we created a new neuron here with these inputs. And let's add the same values here. So minus 0.29. I'm just going to go to minus 30 and then hold shift and go up one. And here minus 0.35. And 1, 2, 3, 4, 5, like this. And the bias here minus 0.26. Like so. This neuron is the same as this one here. You're going to see if we rerun this simulation that both of them are going to blink exactly in the same way. Now we can actually remove these links by right-clicking on them. And this one. And let's move this one on the right. Click on it and connect it to the output. Now reset the bias here to 0. You can press 0 on your keyboard. And you can put any positive weight here. Anything will work. Because basically the value of this neuron here, when it's on, a value of 1 multiplied by any positive weight is going to be greater than 0. So these now are in sync. I'll show you. We go here and refresh, and this is the same thing as before. You can see the same shape appearing here in this diagram. Now this solution here with these neurons works nice for the car on the right, but not for the one on the left. That's the one that we try to fix. So let's create a copy of this and try to modify it so that it works well for the car on the left. I'm just going to click on this and create a new neuron here. And same values, so minus 0.29, minus 0.35, and minus 0.26. So now if I'm going to connect this one up here, and let's set this weight to 0, and this one to 0.1 or anything positive, we get the same thing here. So just to test, this should work in the same way. The car on the right is stopping perfectly. The one on the left still has a little bit of work to do. Let's get this slope to go a little bit like that. So we're going to increase this value here slightly, so holding shift. And basically, I want to get this other car here to slingshot. I don't care if this one breaks anymore. I just want this one to work. And it doesn't really work. It does slingshot a little bit, maybe until here, but it needs to be a little higher. Maybe 26. It's better, but still a little bit more. 24. Even more. Okay, so now it looks perfect. It stops perfect, but the other one breaks. So let's compare now the two functions, and I'm going to put back this high quality diagram here, and let me turn off this one and on the other one. Let's rerun the simulation and see where the car on the right jumps. It's this point right here. And now with the other one, let's see where the other one jumps. It's this point right here. Now turn on this pixelation more because it's really quite slow. And let's create another neuron where we try to define a line that touches both of those points. Let's set this one to 0, this one to some positive value. And here, let's try with this left one first, maybe minus 40, the one on the right minus 90. And the bias here, let's say 60. And now I'm going to teach you how to do the conditional AND. So we want this one and this one to be on, because then this region will essentially intersect with this region, giving us a curve here, not a straight line. So to do that, we put both of these values like this, and you can already see a curve appearing here. But we don't want it like that. We want it at the intersection somehow. So now this is actually an OR, because it's either this one or this one. So we also learned how to do the conditional OR. But to do the AND, we are going to increase the bias here like that. So the value here, if it's on, then it's going to be multiplied by 0.1. So we have 0.1 from here. And if this is on, 0.1 from here. So adding these is going to be 0.2, which is greater than 0.1. But if only one of these is on, like now, then this doesn't turn on because it needs both of them to activate. So let's just try to see how this one works. Probably we need to do some fine-tuning. Yeah, looks like this car is crashing because this is too high. We need to lower it down a bit. So minus 92 maybe. If you look closely, what happens here, it touches that tip a little bit. You can see here, after it stops, it blinks a little bit. So I think that we need to also adjust that one slightly. So here where it says minus 0.40, let's make it maybe minus 0.43. Okay. I think this is perfect. And we don't need this one anymore, because this is anyway connected to 0 here. It was just used as a reference. So let's remove it by right-clicking on this node, then it's going to remove all the other links as well. Now your homework. Go up here and say SPD_3. Try to get it to work for 3 cars. This one seems to be crashing at the moment. One quick note here. I've found many resources claiming you need smooth activation functions to have curves here. One of them in a lecture by a top university. Now, what I'm sure they meant was a smooth curve, because we got a curve here already using a step function. A curve just means something deviating from a straight path. It doesn't necessarily have to be smooth. It may sound like a small thing, but I think that false information like that is confusing, especially because it seems like it should be true. So people pass it around a lot, and it makes understanding things harder, I think. The playground doesn't support smooth activation functions, and as I said earlier, we won't be studying them in this course, but if you're curious, that shouldn't stop you from learning. Nowadays, there are a bunch of resources that can help. Thanks for watching, and see you guys.